In this lecture, we'll talk about how to generate a pulse width modulated signal on a GPIO pin. So how to use the GPIO library, the Python GPIO library, to generate pulse width modulated signals. And there are several functions in the library, and we'll talk about how to use those. So pulse width modulation, as a really quick recap, a pulse width modulated signal is just a square wave. And you can see in the picture we got 3 square waves, right? And the difference between the 3 square waves is what's called the pulse width, basically how long they are high versus how long they are low, the duty cycle. So if you look at these three square waves, all 3 of them have the same frequency, right? If you look at the time when the signal goes from 0 to 1, it's the same on all 3 square waves, right? So they have the same frequency and the same period. But they differ in what percentage of the time their signal is high. So the top waveform, it's high 75% of the time and the low 25% of the time. Then the middle one is 50-50, then the bottom one is 25% high, 75% low. So that's called the duty cycle, what percentage of the time the signal is high. And that's what you want to change with pulse width modulation. You don't change the frequency. You use some constant high frequency, and you modify the pulse width. The whole idea of this is to control an analog device from a digital circuit. So our Raspberry Pi, it generates digital signals, high or low. But there are some devices which respond to analog. But we can't generate analog because we don't have a digital analog converter built in, or not that we can use. So one way to deal with that is to send a pulse width modulated signal. You make the signal go from high to low really fast. Like in this case, maybe it's 500 hertz or something, right? Very fast. Faster than the analog device can respond. So let's say there's a motor or something like that. This motor can't turn off and on at that speed. So what happens is it just moves at a speed that corresponds to the average time that the average duty cycle. So if the duty cycle is 75%, then the average average voltage that the device sees is going to be higher than if the duty cycle is, say, 25%, because it's high much less of the time. So this is basically a digital way to fake out a device that's expecting analog. You can do that with digital. Just make it go high and low really fast, and just change the percentage of time that the signal is high or low. So let's go through the libraries that we use to generate pulse width modulated signals. First thing you want to do, if you want to generate a pulse width modulated signal on a pin, you've got to mark that pin. You have to basically declare that pin is going to be used for pulse width modulation. And this does something inside the processor that we don't need to talk about. But you have to call this function GPIO.pwm. Now, GPIO.pwm, it takes 2 arguments. First argument is the pin that you want to set pulse width modulated signals on. And the second argument is the frequency of the pulse width modulated signal that you want to generate. So in this case, we're saying, look, pin 18 is going to get a pulse width modulated signal. Its frequency is going to be 400 hertz. Now, note that when you call this function GPIO.pwm, when you call this function, it does not right then and there generate the pulse width modulated signal. This only changes the internal connections inside the processor so that pulse width modulated signals can be generated on pin 18, but it doesn't actually start generating it yet. There's another function for that. Another thing to note about this function GPIO.pwm is that it actually returns an object, PWM OBJ we're calling it. PWM OBJ equals blah. So that object is what you're going to use to make your method calls in the future. So this is easier shown. So we've been sort of skirting this idea of object-oriented programming. We talked about it a little bit, just very briefly, but we're not getting heavily into it. But here, it comes up again here. What happens is this PWM OBJ is an object of a particular class, and we can make method calls. We can call functions that just apply to that object. Okay, so it's easier if I just show you. So once you make this PWM OBJ object, now maybe you want to start generating a pulse width modulated signal. So how do you do that? You call start function. Now it's a method. This start method, the call is prefixed with PWM_OBJ. So whatever object you got returned from that GPIO.pwm call, that object, you call this start function on that object. So PWM_OBJ.start 100 takes one argument, in this case 100. So that argument indicates the pulse width, the duty cycle. So the duty cycle goes from 0 to 100, 0% to 100%. So 100 duty cycle means it is high all the time. If you gave it 0, that would be low all the time. If you gave it 50, you'd be high half the time, low half the time, and so on. So once you call that start function, that actually starts generating the pulse width modulated signal on the pin. Now, once you start generating a pulse width modulated signal, you can change the pulse width if you want to while you're generating it. And for that, you call change duty cycle. Again, you call it on the PWM-OBJ object. So PWM-OBJ dot change duty cycle 50, that just assigns a new duty cycle of 50. So now I've changed it from 100 duty cycle, high all the time, to a 50-50 duty cycle, high half the time, low half the time. You should note that the frequency is not accurate on these Raspberry Pis. So actually, this is very different than the Arduino. The frequency that you get is not too accurate, and it can be off by a lot, by over 50% when you get to higher frequencies. Just know that, okay? What that means is that if you really need tight pulse width modulated control, you're going to have to do something else. There are other ways to go about it. You can't use the standard library functions if you want accuracy on a Raspberry Pi. And part of the reason why you get this inaccurate behavior is because you're using an operating system. The operating system has these delays that are hard to know and hard to predict, where the Arduino has no delays, so it's much better in terms of real-time performance. You can get the delays that you want directly. You can do it too with the Raspberry Pi, but you almost have to circumvent the operating system in a way that we'll talk about actually next course. Now, frequency control. These pulse width modulated signals, when you generate them, you generate them at a particular frequency, right? So you can assign the frequency when you mark that pin for being a pulse width modulated signal. When you call GPIO.PWM, you pass the frequency that you want, 400, say 400 hertz. But you can't change that frequency once you've created it, not easily. You can't just say, okay, now I want to go to 500 hertz, 600 hertz. Now, if you're using pulse width modulation, you don't need to change the frequency. But it is nice to be able to change frequencies because maybe you want to make tones. Maybe you want to make beautiful music, okay? And you want to make different sounds, different frequencies. And then it would be nice to be able to have a square wave whose frequency you could change. Now, if you remember in Arduino, we did this. We had a tone function. And this tone function, you couldn't change the duty cycle. It was always 50-50. But you could change the frequency. And then we hooked it up to a buzzer and made different sounds, different frequency sounds, right? So that was very convenient. You don't have a built-in function for that in the GPIO library. So what you have to do if you want to do that, if you want to make something where you change its frequency, you have to do it manually. Okay, do it the hard way. So what I mean by that is you actually have to adjust the delays to make it the frequency you want. So here's an example. You got your infinite while loop. GPIO output 18 equals true. Then you sleep for 0.5 seconds, half a second. GPIO output 18 false, then you sleep for another half second. So what this gives you is a square wave, high, low, and whose period is 1 second, right? Because you slept for half a second, so you got a 1 second period, which means a 1 hertz frequency. So this gives you a square wave with a 1 hertz frequency. So by changing those time values, you can change the frequency manually, right? You can compute what the period should be, and you make the time value half of that, and then you can get whatever frequency you want. So if you want more accurate frequency control, you're going to have to do, if you want to be able to change frequency control easily, you're going to have to do this manually. Thank you.